Hey, welcome back. In this video, we're going to continue discussing induction, but we're going to look at a different kind of induction. Instead of looking at weak induction, like we have been in the previous videos, we're going to look today at strong induction. So the last few videos, we've been looking at weak induction, which you can visualize kind of like dominoes, where you start with the first domino. That's your base case. And then each domino knocks down the next domino. And that's your inductive step. We used weak induction on a bunch of different example problems, including problems where we had to simplify summations. For example, sums of polynomials and geometric sums. We also used weak induction to prove the inclusion-exclusion principle in full generality for any number of sets. And we saw a bunch of example problems where we use the inclusion-exclusion principle for 2 or 3 sets and apply it to poker hands. So in this video, we're going to focus on strong induction, and we're going to use it on a bunch of different kinds of problems where strong induction is more useful than weak induction. Like I said in class, any proof that you do with weak induction, it's possible to also do that proof with strong induction. It's just that sometimes there's no need to do strong induction. But if you want to do strong induction, even if you don't have to, it's fine to use it if you really want to. So let's talk about what is strong induction and what's the difference between strong induction and weak induction. So the proposition P of n, that we have in strong induction is the same kind of proposition that we have in weak induction. P is just a property of the natural numbers. So for example, P of n could be the proposition that n is divisible by 1. Now, the axiom that we have here for strong induction differs from weak induction, and it differs in one specific place. So let's look at it. So we have a base case here, and here it's the same as weak induction. So I'll write the weak one down here. Here's our strong, here's our weak. Base case for weak induction is the same. Now, here's our inductive step. And here's our conclusion. Weak induction also has the same conclusion as strong induction. So over here, we end up with the same part. For all n greater than or equal to 0, we get P of n. The difference, though, is in that inductive step. So the quantifier in front, the for all n greater than or equal to 0, that's still common between the two. And the end of it is still the same. The P of n plus 1. But the main difference is in this first part right here, which I'll put in a box. Bring a little arrow to that. That's our inductive hypothesis. And that's the key difference between strong induction and weak induction. In strong induction, we have a stronger inductive hypothesis. In weak induction, we have a weaker inductive hypothesis. What do we mean by that? Well, here's our inductive hypothesis in weak induction. It's just P of n right there. Our inductive hypothesis in the strong induction is this conjunction, I equals 0 to n, of P of I. Another way we can write that conjunction is P of 0 and P of 1 if n is greater than or equal to 1, and P of 2 if n is greater than or equal to 2, all the way up to and P of n. So our inductive hypothesis, this is what we assume to prove the inductive step. With strong induction, we assume P of 0 and P of 1 and all the way up to and P of n is true. With weak induction, we only assume that P of n is true. So we get way more assumptions with strong induction. That's why I say that our inductive hypothesis with strong induction is stronger. So it makes sense why it's called strong induction and the weak induction is called weak induction. I'll mention, like I did in the video for weak induction, that the quantifier, the for all n greater than or equal to 0, it ranges over the natural numbers. And the natural numbers are 0, 1, 2, and so on. And I'll mention one more time, the key difference between weak induction and strong induction is just that conjunction. The one that I pointed out earlier, the conjunction from I equals 0 to n of pi. So this part right here, that's the only difference between the weak induction and the strong induction. Now, just like weak induction, we can start strong induction from any non-negative integer. In fact, we can start it from any integer we want. So we can, instead of starting our base case at P of 0, we can start it at P of k here. And our inductive step will be a little different. So instead of our inductive step being for all n greater than or equal to 0, it's going to be for all n greater than or equal to k. So we're going to do an inductive step for all n starting at k instead of starting at 0. And we just go up from there. And this part right here, same as on the previous slide. This part right here, the only difference is the k instead of the 0. So it's not too surprising. Just like we saw with the weak induction, we can start elsewhere instead of starting from 0, and the process is the same. So here's an example of a proposition that we might want to prove with strong induction, where we wouldn't be starting it at 0, we would want to start it at 2. And the proposition is that n is a prime or a product of primes. So let's actually see how we can prove that proposition for all n greater than or equal to 2 using strong induction. Before we prove it, let's discuss what it means to be prime. So our definition, we'll say that an integer n greater than or equal to 2 is prime, and if and only if its only positive integer divisors are 1 in itself. In other words, the only positive integer divisors of n are 1 and n. In that case, we call it prime. Otherwise, it's not prime. And notice that we're requiring n to be greater than or equal to 2. So we're not talking about 1 here. We're only talking about the integers n greater than or equal to 2. So here's an important observation about integers greater than or equal to 2 that are not prime. We can write them as a product a times b for some integers a and b that are both greater than or equal to 2. We're going to use that later on this slide. So here's the thing we're trying to prove. For every integer n greater than or equal to 2, how can we show that n is prime or a product of primes? Our base case here will be n equals 2, which makes sense because we're trying to prove this property for all n greater than or equal to 2. And with 2, we see that 2 is a prime. So we got the property we want for 2. Our strong inductive hypothesis will be that each integer, 2 up to k, is a prime or a product of primes. And now we have to look at k plus 1. We consider a couple of cases for k plus 1. If k plus 1 is a prime number, we're done. Then we have the property we're looking for. Otherwise, we can say k plus 1 is not prime. In the case that it's not prime, we can use the property that we observed in the second bullet on this slide. We can say that k plus 1 is equal to a times b for some integers a and b that are greater than or equal to 2. Also note that if k plus 1 equals a times b for some integers a and b greater than or equal to 2, then we also have that a and b are both strictly less than k plus 1. That means that we can use the inductive hypothesis on a and b, which means that a and b are both prime or a product of primes. This immediately tells us that since k plus 1 is the product of a and b, then k plus 1 is a product of primes. So here's another question for you to think about. Suppose that you were given a candy bar. The candy bar has n pieces for some integer n greater than or equal to 1. How many places on the candy bar do you have to make breaks to separate the bar into n individual pieces? And make sure you prove your answer, maybe using induction. Notice with this problem, and the last problem that we looked at on the previous slide, if you're going to do induction on it, you're going to take the case of n and break it down into smaller cases. And that's what generally happens with strong induction. You can take your case of n and you can break it down into smaller cases. This is also what's happening with weak induction. We take the case of n and we break it down into smaller cases. However, the way that we break it down in weak induction is much more specific. In weak induction, we break down n into smaller pieces by taking off the last part and breaking it down into a part that's the n minus 1 part plus the last part. So that's typically what we do with weak induction. We're just taking off the last part, reducing to the n minus 1 part. With strong induction, there's a lot more possibilities for how we break down the n. Here's one more variant I wanted to mention for strong induction. It's very similar to the previous one we saw. It's just that the base case is a bit different. So our base case here allows multiple cases in it. So on the previous slide, our base case was just P of k. Here, our base case includes P of k plus 1, up to some P of k plus c for some positive c. Notice that this also slightly changes the inductive step. So for the inductive step, our quantifier here, it starts from k plus c instead of from k. And our inductive hypothesis is still the same. We assume that all of the PIs are true from k for I equals k up to n, where n, again, is greater than or equal to k plus c. And we use that to prove P of n plus 1. And this is for all n greater than or equal to k plus c again. And we still get the same conclusion that we got on the other slide where we saw the variant of strong induction where we start at k. So for all n greater than or equal to k, we can conclude that P of n is true. So again, the main difference is just the base case. We can have multiple cases in our base case. And that means that our inductive step, we can start that from k plus c instead of from k if our base cases go up to k plus c. So like I said, that conjunction for the base case just means that the base case can include multiple cases, multiple integers for our base case. And here's an example proposition where we can prove it with strong induction, and we would want to include multiple cases in our base case. So the proposition is that if the sequence A sub n is defined by A sub 0 equals 1, A sub 1 equals 2, and A sub n plus 2 equals 3 times A sub n plus 1 minus 2 times A sub n for each n greater than or equal to 0, then A sub n equals 2 to the n. So let's see how we can prove that with strong induction. And here, our base case is going to have two cases. It's going to be the 0 case and the 1 case. And we'll see that will mean that our K up here in the strong induction, this K, for this specific problem, will be a K equals 0. And the C will be, so this C right here, and this K, the C would be a 1. So that would be two cases. It's going to be a conjunction I equals 0 to 1 of P of I. And this right here, that was always a 0. Okay, so let's see how we can prove that. Before we prove it though, we should probably discuss a little bit of terminology. So we're going to talk about linear recurrence equations in this video and in the next video. In the next video, we'll actually see how to find explicit formulas for them. But in this one, we're just going to apply strong induction to prove some explicit formulas for them. So first, we're going to define a recurrence equation without the linear part. This is just going to be an equation that defines a sequence recursively. The linear recurrence equation is going to be a recurrence equation for some sequence. We'll give the sequence a name, A1, A2, A3, and so on. It's not important that we named it with A's. You can name it any letter you want. And this recurrence equation defines A sub n as a linear polynomial of A sub n minus 1, A sub n minus 2, A sub n minus 3, and so on. And another way to say a linear polynomial is a polynomial of degree 1. So here's an example of a linear recurrence equation. A sub n equals A sub n minus 1 plus A sub n minus 2. That's a linear recurrence equation. Here's one that's not. If you have A sub n equals A sub n minus 1 squared plus A sub n minus 2, that is not a linear recurrence equation because the 2 right there, that's not linear. That would be a polynomial of degree 2, not degree 1. So that would be a problem. Notice that the linear recurrence equation in the third bullet, the A sub n equals A sub n minus 1 plus A sub n minus 2, that's the linear recurrence equation for the Fibonacci sequence. And we'll talk more about that sequence later. There's also a lot of other sequences that have that exact same linear recurrence equation. The way to make it the Fibonacci sequence is to choose specific values for A sub 1 and A sub 2, or A sub 0 and A sub 1, depending on where you want to start the sequence. And if you don't choose the initial values for the Fibonacci sequence, like 1 and 1, you'll get a different sequence. So here's the problem that we saw on the previous slide. Let's see how to prove this with strong induction. We have a sequence A sub n. It's defined by A sub 0 equals 1, A sub 1 equals 2, and A sub n plus 2 equals 3 times A sub n plus 1 minus 2 times A sub n. And this is defined for all n greater than or equal to 0, always was 0. Then we have A sub n equals 2 to the n. So let's try to prove that. We'll prove it using strong induction. So our base case, like I said before, instead of just having a single integer value in it, we'll have two integers. We have a sub 0, which by definition is equal to 1, and 1 is 2 to the 0. And a sub 1 is defined as 2, and that's equal to 2 to the 1. Now here's our strong inductive step. We'll assume that a sub I equals 2 to the I for each I equals 0, 1, up to k, where k is some integer that's greater than or equal to 1. Now, a sub k plus 1, we want to show that that's equal to 2 to the k plus 1. In order to show that, we can use our linear recurrence equation. We can say a sub k plus 1 equals 3 times a sub k minus 2 times a sub k minus 1. Now we can plug in our strong inductive hypothesis. We know that a sub k is equal to 2 to the k. We know that a sub k minus 1 is equal to 2 to the k minus 1. So 3a sub k minus 2a sub k minus 1, we get 3 times 2 to the k minus 2 times 2 to the k minus 1. And that simplifies to 2 to the k plus 1, exactly what we wanted. So here's a problem for you to think about. And this one, it might have a solution that's pretty similar to the last one. We have another sequence here. A sub 1 equals 1, a sub 2 equals 3, and a sub n plus 2 equals 5 a sub n plus 1 minus 6 times a sub n. And this is for n greater than or equal to 0. And here's the problem. Find with proof an explicit formula in simplest form for a sub n. And find a formula that does not use any recursion or summations. So find the simplest possible formula for a sub n. Okay, before we finish this video, let's look at one more kind of problem that we can do with strong induction. These problems, we can call them coin problems. So suppose that we have two different kinds of coins, and we have unlimited coins of each of these kinds. One of these kinds of coins is worth $3. Again, we have unlimited of that kind of coin. The other kind is worth $5, and we have unlimited of that kind as well. And the question is, what is the greatest integer number of dollars that we cannot make using these coins? So at least in this class, we never saw a problem like this before. So what do we do when we have some problem about integers, positive integers, and we never saw a problem like it before? Well, it doesn't hurt to look at some small values, some small positive integers, try to come up with some good guesses. So let's try that. So we'll look at some small integers together. We'll try to figure out a good answer. So we can see if our coins are worth $3 and $5, we cannot make $1 or $2 because those numbers of dollars are smaller than the numbers that we have for our coins. We can't split up our coins or anything. We only have whole numbers of coins, so can't make any number of dollars that's smaller than 3. Okay. We can, of course, make $3 because we have the $3 coins. We can't make $4. There's no way to make $4, clearly. $5, though, we can definitely make that with the $5 coins. $6, that one we can make. So $6, 6 equals 2 times 3. So 2 $3 coins, we get $6. So that's fine. $7, that one, we can think about that a little. We see, can't make that. You can look at all the combinations, can't make 7 with $3 and $5 coins. $8, we can totally make $8. So we can see 8 equals 3 plus 5. So we take a $3 coin and $5 coin, we get $8. $9, we can totally make that. 9 equals 3 times 3. 10, we can also make 10. So 10 equals 2 times 5. 11 can also be made. So 11, notice that one is 2 times 3 plus 5. 12, 12 can clearly be made because that one's just 4 times 3. And finally, let's look at one more. 13. 13 is just 2 times 5 plus 3. And we can kind of keep on going like this. And we can notice that 13, we compare that to 10. It's just with the extra $3 coin on there. 12, we can compare it to 9. Again, it's an extra $3 coin. 11, we can compare to 8. And look, it's an extra $3 coin. That's the only difference between them. So we can kind of look at this pattern, and we can try to use this to prove that the answer we're looking for is 7. So the largest number of dollars that we cannot make using the coins, it looks like the answer is 7. We just need to prove that. So let's try to prove that using strong induction. So there's the problem again. It looks like the answer is 7, just based on the work we did on the previous slide. We try to prove it now. We have 2 things to prove. We need to prove that 7 is impossible. In other words, we cannot make $7 using $3 and $5 coins. And then we need to prove that every integer greater than 7 is possible. In other words, every integer greater than 7 can be made with $3 and $5 coins. So let's give a little more reason why 7 is impossible. 7 is impossible because 7 is not divisible by 5. So you can't make 7 with $5 coins. 7 minus 3 is not divisible by 5. So you can't make 7 with one $3 coin and $5 coins. 7 minus 2 times 3 is not divisible by 5. So you can't make 7 with 2 $3 coins and any number of 5s. And obviously, we can't make 7 with more than 2 $3 coins. So 7 is impossible. Now, we have one other thing to prove. We saw that 7 is impossible. Now we need to show that every integer greater than 7 is possible. So we start with 8. 8 we saw already is 3 plus 5. 9 is 3 times 3. 10 we saw is 2 times 5. And that's our base case for our strong induction. So this time our base case had 3 cases. And the previous problem, our base case had 2 cases. It's fine. It can have any finite number of cases. So you might see some problem where it has like 2,000 cases. That's fine. Hopefully those cases can be done in some similar way for all of them. Otherwise it would be real annoying. Okay, so our base cases were 8, 9, and 10. So our value of K was 8. Our value of C was 2. And for the strong inductive hypothesis, we're going to assume that each integer number of dollars I, where 8 is less than or equal to I is less than or equal to K, can be made using the $3 and $5 coins. So the property is possible for all I with 8 less than or equal to I less than or equal to K. That's our strong inductive hypothesis. Also, we're going to assume that K is greater than or equal to 10. So K is going to be the upper bound of the range of the integers for which we know that the property is true. So the range of the integers for which we know the property is true, it starts at 8, it goes up to K, and we want to prove our property for K plus 1. So we're assuming that it's true for 8 up to k, and we're going to prove it for k plus 1. So in order to show that it's possible to make k plus $1 using the $3 and the $5 coins, all we have to do is we can use that pattern we saw on the previous slide. We compare k plus $1 to k plus 1 minus $3. K plus 1 minus 3 is k minus 2. We know by the strong inductive hypothesis that k minus $2 can be made with $3 and $5 coins. This is because k is greater than or equal to 10, which means that k minus 2 is greater than or equal to 8. And so that's covered by our strong inductive hypothesis. So k minus $2, it can be made with $3 and $5 coins, which means that k plus $1, we can make that the same way that we make k minus 2 with $3 and $5 coins, where we just add an extra $3 coin. So we take whatever way we made k minus 2 with $3 and $5 coins, and we just add an extra $3 coin to get k plus 1. And that's because k minus 2 plus 3 equals k plus 1. Here's a similar kind of problem for you to think about. Suppose that you have unlimited coins and they're each worth $2 or 2k plus $1 for some positive integer k. Positive integer means starting at 1, 2, 3, and so on, not including 0. So the problem is to find the greatest integer number of dollars that you cannot make using these coins in terms of k. And here's another problem. Suppose here that you have unlimited coins, each worth $4 or $7. For this one, same question. What is the greatest integer number of dollars that you cannot make using these coins? Thanks for watching.